This is the Algebra 2 work number 97, just the even solutions. You can look up in the back of the textbook the odd answers. You won't have all the work shown, but you'll have at least the answers to look at. So, for these problems, in the first one, you're going to multiply that. It's squared, so it's the first term squared and the last term squared, and twice their product. Number 12, you're asked to find the conjugate. Well, you've got -4 plus 8i. The conjugate would be -4 minus 8i. And you can see the conjugate for number 14 right there. Pause the video at any time if you need a little extra time to look at the solutions or re-watch them being worked out. For number 16, you're multiplying a conjugate pair. So remember, that's the sum of the two squares. Number 17, another conjugate pair. Oops, number 17 is odd, and you didn't even have to do it. But there it is for you to look at. Number 18 is another conjugate pair, the sum of two squares. And then number 20 is one where you have to multiply by the conjugate of the denominator so that you're rationalizing the denominator. And don't forget to answer in the proper format, the a plus bi. So you see the final answer, -37 50/3 minus 50 50/3 I. In number 22, you're doing the same idea here. You're going to eliminate the radical in the denominator, the I, which is a radical, by multiplying by its conjugate and then simplifying. In number 24, the reciprocal of -i is 1 over -i. Now we have to eliminate that I in the denominator. And 26 is the same idea, that when we ask for the reciprocal, we end up with an I in the denominator, a radical. So we multiply by the conjugate to eliminate that complex number, the imaginary number there, and you can see the problem worked out. Now we're into 710, and again, I'm only doing the even answers. So in this first one, I'm going to pause this, the work. It's asking you if this is a solution, so you're going to plug it into the equation to verify that the left-hand side of the equation does in fact equal the right-hand side. So we plug in 4i into the equation, and now I'm starting to plug in -4i, and you'll see that it does work out for both of them. For number 4, we're plugging in that solution into it, and it doesn't work. It's not a solution. I'm going to pause the video for a minute there. When I plug it in, I end up with -3 plus 2, which is not zero. I don't even need to check the other one. If one of them doesn't work, then its conjugate, because you'll notice those are conjugate pairs, positive I root 3 and negative I root 3, those are conjugates. If one of those conjugates doesn't work, neither will the other. And this one we have a conjugate pair again. We plug it in, and you're going to have to do some multiplying of the binomial and distribution and collecting like terms, and you find that yes, indeed, the left side does equal the right side. It does equal 0 in both those cases, and so 2 plus I and 2 minus I are indeed solutions to the problem. And here, this time, we're asked to write an equation that has 7i and -7i as solutions. So we go back to the idea of when we were factoring quadratics. We knew how to do that. We showed you that in class today. And now here's another one where I have these two numbers. Now, I'm going to pause this at a certain point, right, after we distribute and collect. Now look at that. I have x minus 4 minus 3i, and I have x minus 4 plus 3i. This is actually a conjugate pair. I'm going to group the x minus 4, and that is the first term. X minus 4, the group of it, is like my a. And then minus 3i in the first one and plus 3i in the second one. So it is a conjugate pair. And when you multiply the conjugate pair, you get the first one squared plus the last one squared, because it's a conjugate pair of complex. Much easier way to simplify these problems. Number 12 is done the same way. After I distribute the negative, I have those groups, x plus, minus 2. And then I can see I have a conjugate pair. Again, when you have a conjugate pair of imaginaries or complex numbers, you always get the sum of the two squares. So I have the first group, x minus 2 squared, plus the second one, which is square root of 2 squared. And then I simplified. Number 14, it's once more the same type of problem. I distribute the 1, and then I notice I have conjugate pairs. I get the first term squared plus the last term squared. Simplify it all out, and there's the end of all of the even solutions.